This meeting is now being recorded.
Hello, and welcome to today's webinar, the fourth in the Measurement Error webinar series. I'm Reagan Bailey from the Office of Dietary Supplements at the National Institutes of Health. I'll be moderating today's webinar, in which we'll continue the theme of estimating usual intake distributions with Dr. Kevin Dodd. A few notes before we get started. This webinar is being recorded so that we can make it available on the website. All phone lines have been muted and will remain that way throughout the webinar. There will be a question and answer session following the presentation. You can use the chat feature to submit a question. And finally, a reminder that you can find slides for today's webinar on the website that has been set up for series participants. The URL has been sent out via the listserv and appears in the notes box at the top left of your screen. Other resources available on the page include the glossary of key terms and notation and the recording of the first 3 webinars in the series. As I mentioned, our presenter for today's webinar is Dr. Kevin Dodd. Kevin is a mathematical statistician in the Biometry Research Group, Division of Cancer Prevention at the National Cancer Institute. Kevin was involved in the development of the Iowa State Method and the National Cancer Institute Method for modeling usual intake. He has worked extensively with population-level survey data, most often the National Health and Nutrition Examination Surveys. Today, Dr. Dodd will talk about accounting for complex survey design and estimating usual intake distributions. Welcome, Dr. Kevin Dodd.
Thank you, Reagan, and thank you to all of you on the phones that have joined us today. Before I go on, I want to remind everyone that this series is organized by a bunch of collaborators from a diverse collection of institutions that I've shown here on this slide. The nutritionists and statisticians listed on this slide have been working together on the topic of measurement error and self-report dietary intake data for many years now. And the series as a whole is dedicated to the memory of our colleague, Arthur Schatzkin, who was instrumental to all the progress this area of research has made over the years. We've previously mentioned that the webinar series as a whole covers 2 main areas of interest. The first is in describing usual intake distributions, where we might want to know the mean usual intake in the population, or the 25th percentile, or the proportion of the population with intake below some threshold. The second topic would be concerned with estimating the relationship between diet and some health outcome. Now, in this case, we might want to know the slope of the regression line that goes through this cloud of points here. Today's webinar introduces concepts that are mostly applicable for the first case, for distributions, but may also impact the way you would address the second case, depending on how your data comes to you. I'll start off by showing you this figure that was taken from the latest Dietary Guidelines Advisory Committee report, which shows for a bunch of nutrients, micronutrients, and the estimated fraction of the U.S. population with usual intake that meets or exceeds the estimated average requirement, also known as the EAR for those nutrients, based on the reported food consumption, i.e. it's not incorporating the effect of dietary supplements. So this table, along with a lot of other information, was used to formulate guidance about how best to eat a healthy diet. Now, the main thing I want to draw your attention to in this slide is this little line of text down in the lower left corner that says where this data that went into this figure actually came from. It actually came from the dietary portion called the What We Eat in America portion of the 2001-2002 National Health and Nutrition Examination Survey, or NHANES, which I consider to be the U.S.'s flagship diet and health survey. The NHANES is a really big undertaking. It's a large-scale survey that's designed to be nationally representative, and the data are collected from all over the United States according to a complex sampling plan. Now, these sorts of complex national level surveys happen in other countries as well, and I think it's fair to say that they provide the bulk of population monitoring data. In fact, when a lot of these methods we've been talking about for estimating usual intake distributions were being developed, there's always the sense that eventually they're going to have to be applied to these kinds of survey data. Now, the webinars so far have primarily focused more on the actual development of the methods and how they'd be applied to a data set of, say, 24-hour recalls, but it pretty much skipped over talking about exactly how the researcher, i.e. you, is supposed to get their hands on this data, kind of data. Now, today's webinar, I'm going to focus on details related specifically to data collection and also the details on how collecting data using the survey sampling methods I'll be talking about here affects the analysis you can do with these modeling approaches. So there's two broad objectives to this webinar that I've listed here on this slide. The first objective is to describe three general elements that either separately or in combination comprise a complex survey sampling design. What makes a survey design complex? And these three elements are stratification, clustering, and weighting. And I'll talk about each one. And each of these elements has to be accounted for when you actually analyze survey data. Now, the second objective of this webinar is to identify some statistical techniques for variance estimation that are very important in the analysis of survey data in general and in the analysis of usual intake distributions in particular. So this slide shows here in a little more detail the order that I'm going to address these two objectives that I just talked about. And this will be the little, this is how we'll walk through the webinar. So first, let's talk about what makes a survey sampling design complex. Well, intuitively, a complex design is one that's the opposite of simple. Now, most of the time, when statisticians are coming up with a new way to analyze data, they start off with a simple case called, appropriately enough, simple random sampling. Under simple random sampling, the data you have at hand are selected from the population of interest completely at random. And that means that every member of the population has an equal probability of being selected. Now, before you can actually pull people out of the population to get into your sample, you have to get a list of the population members. Now, in survey sampling language, this list of members is called the sampling frame. Now, if your population of interest is a small, homogeneous group, it's pretty easy to obtain a simple random sample. And as I just mentioned earlier, it's going to be very easy to analyze the data you get because most of your statistical analysis techniques were developed just for that simple random sampling case. So here's a diagram showing how you might select a simple random sample of 20 people from the population represented by the 100 symbols in the box on the left. So once you have a list of all 100 members in the population, which in this case is the numbers from 1 to 100, with 1 corresponding to the top left position and 100 to the bottom right, you just randomly jumble up all the numbers and take the first 20 out of your jumbled set. And the chance that any one person in the population gets selected is 20 out of 100 because you're taking 20 out of 100 names, or 20%. So in the population box, I've highlighted the individuals in white that are going to be selected into your sample, shown in the box on the right. So you see that the third person in my sample is person number 15 from the population. Now, like I said, this might be practical in some cases where your population is easily accessible, but in practice, especially at a national level, data don't come to you this way. Instead, they're collected under a complex survey design. Well, why would you use a complex survey design to pull your data? Well, a lot of times it comes down to cost. Either the cost involved with drawing up the desired sampling frame and figuring out how to contact your participants, or the cost of traveling around the country actually collecting the data for the people that have agreed to be in your sample. Now, another reason for collecting data with a complex sampling plan is to improve the precision of subpopulation estimates by making sure that you have enough people in certain demographic subgroups to allow separate estimation within those subgroups. So a minute ago I said there are these three elements that can make a sampling plan complex: stratification, clustering, and weighting. I'm going to talk about each one in turn in the following slides, but often you'll see more than one or even all three elements used in the development of a complex sampling plan. When I talk about the general case of the general complex survey design, I mean one that has all three of these elements involved. So first, stratification. In the last two webinars, we've talked about performing stratified analyses to get subpopulation estimates. Well, that's what we're talking about here. Stratification means grouping individuals in the population into more homogeneous groups that share specific characteristics, usually demographic characteristics. And you usually do this in the context of identifying subpopulations of a priori interest. For example, pregnant and lactating women, or children, or low-income individuals. Now, for the next few slides, I'm going to be showing some examples of how you might incorporate stratification into your sampling plan. Now, in this example, I'm going to rely on this diagram here, which shows a population of interest And I'm going to assume, and for my example, I'm going to suppose that this population of interest is comprised of 4 important subpopulations, or strata, of different sizes as shown here. 40% of this hypothetical population fall into stratum 1, 30% in stratum 2, 20 in stratum 3, and 10% in stratum 4. So now my diagram from a few slides back is a little bit different. Now I've indicated that my population has 4 different kinds of people in it, and I've used different symbols and colors to identify people in the different strata, and I've labeled them along the left-hand side there as to which strata they belong in. So the sampling frame is still the numbers 1 to 100, but now under this setup, members 1 through 40 are in stratum 1, members 41 through 70 are in stratum 2, and so on. We can draw the exact same people from this population that we did before under the simple random sampling idea, where we pretend that the population is homogeneous, and all we need is a simple random sample. So here, the third person in my sample is still person number 15. But now, in contrast to what I did before, I'm keeping track of the stratum membership for each sampled person. One nice thing about this simple random sampling idea is that it results in a sample that reflects the population. Our sample actually retains the same proportions in each stratum as are present in the population, at least on average. Now, depending on the size of the population, the size of your sample, the number and size of your strata, you can get unlucky with a sampler or two and end up with a sample that's not exactly a miniature version of the population, but in this case, that didn't happen. But there's a downside to the simple random sampling approach, and that is that you end up with very small expected sample sizes for these small strata, and so the resulting subpopulation estimates won't be based on much data and will therefore be imprecise. So, for example, in this case, your estimate for stratum 4 would be based on just these bottom 2 people in the lower right corner, the absolute minimum that you would need to even compute a variance estimate. And if you got unlucky under a different randomization, you might not even have anyone in your sample from stratum 4. So how can the stratification be incorporated into a sampling plan to help offset these kinds of problems? Well, one way to help maintain a given precision for all your subpopulation estimates would be to ensure that you always draw the same number of people from each stratum of interest. So this slide shows a different sample selection scheme, where now my sample of size 20 draws 5 people from each stratum. So here, because it's a different randomization, the second person in my sample is population member number 16. Now, under this sample selection plan, we do keep our equal sample sizes for all our strata, so we have the same amount of information with which to make subpopulation estimates. This doesn't guarantee exact equal precision of those estimates. If some strata have more variability than others, you won't get equal precision. But at least you can avoid the situation where you get really unlucky and have some strata are completely missing representation in your sample. What are any downsides of this approach? Well, yeah. Under this hypothetical balanced stratified sampling plan, we've lost a property we said was nice about simple random sampling, because now the stratum distribution in our sample doesn't match that in the population. Because now we have 25% in our sample from each stratum, and that's not how the population that's not the population distribution of these different strata. In fact, we've actually undersampled strata 1 and 2 while oversampling strata 3 and 4. Now, if we want to get a whole population estimate instead of just our subpopulation estimates, we'll have to account for this over and undersampling. So there are trade-offs to be made when you introduce stratification in your sampling design. Compared to simple random sampling, you can end up with more precise estimates for small strata, but at the expense of having less precise estimates for large strata. Now, I just want to point out, this is just an example showing how one way the stratification can work. In practice, stratified sampling doesn't have to be balanced. There may be more trade-offs to be made. For example, you might be in a situation where some subpopulations are of more interest than others and therefore need more of the sample allocated to them to make sure you get good estimates. So now we'll talk about the second element that's often incorporated into complex sampling plans, clustering. Clustering refers to sampling of multiple individuals within the same area. Usually by area we mean geographic, like a neighborhood or household, but it could also mean sampling people within the same family, regardless of location. For example, if you're looking at genetic factors. One reason that clustering is often used in complex samples, especially in U.S. studies like NHANES, is that it cuts down on data collection costs that are associated with travel. You can set up an exam center in a particular city and get a lot of people to come to the centers as opposed to having to travel all over the country to get one person at a time that you would if you were doing simple random sampling of people. So let's return again to our stratified population example, but now I've overlaid the black irregularly shaped boxes in the population that separate people into smaller groups. And this is my clustering, okay? Now, with cluster sampling, I don't take individual people. I take all the members of a cluster at a time. So my 5 people in the first row of the sample box on the right come from taking all of the members of the 2 circle clusters shown in the left, where the members have been shaded out in the white. Now, an important thing to know about observations from individuals sampled from the same cluster is that they tend to be correlated. Now, this is in contrast to simple random sampling, where individual observations are treated as independent pieces of information. The correlation in this cluster sampling reduces the effective number of these independent pieces of information. So you get a loss of precision in your estimates. You may have the same number of people in your cluster sample, but some, and hopefully small, portion of that information can be considered redundant, and that's because of this correlation going on. It's possible to extend this clustering idea to several levels, and that leads to what's called multi-stage sampling, where you subsample clusters of smaller units from your first level clusters. Now, the first stage clusters are sometimes called primary sampling units and often abbreviated as PSUs. And when you do statistical analysis, usually it's that first level of clustering that really drives the precision of your estimate. So in practice, analyses of multi-stage samples sometimes ignore the effects of the other stages of sampling, or other stages of clustering, sorry. So this is a schematic representation of a multi-stage design. It's similar to what gets used in the U.S. Enhanced Survey, where the first stage of sampling selects counties within the United States, and then selects smaller geographic regions called segments that are made up perhaps of census block groups, is another term that's used in this kind of sampling, and then goes after households within those selected segments, and then finally samples individuals from the selected households. So I said before that incorporating these survey design elements can decrease the costs associated with drawing up your sampling frame and figuring how to contact prospective participants. Well, this is what I mean by that, or this is an example of that. With multi-stage sampling designs, like the one in NHANES, you can build up your sampling frame in a stepwise manner. So first you go get a list of counties, and then draw your first stage sampling units. Then you just go get more details on just those counties you selected to pick your second stage units, made up of census block groups. Then you go, once you have that second stage list, you go focus on getting details of the households just in those block groups that you need, and then focus on getting contact information for just those households that you need, that you select. And this eliminates the need to have some big, enormous, complete listing of the contact information for every household in the country. You can build it up piece by piece like this. So you can cut down on the cost of drawing up your frame and getting people to agree to be in your survey, but you can also greatly reduce the cost of collecting the data from participants. For example, NHANES participants come to what's called a Mobile Examination Center, or MEC, that's actually a collection of trailers that gets hauled all over the United States. And when you keep the number of stops down to a reasonable number by doing this clustering idea, that lets NHANES direct the resources into getting data, not into getting fuel for their trailers. So the last element of complex survey designs I want to talk about is weighting. Weighting gives an indication of just how many people in the population a given sampled individual represents. And the way you construct these weights is as follows. Each individual in the final sample obtained from a survey design has a sample weight that's equal to the inverse of the final probability of being selected from the population. For the simple random sample that I showed you in the example earlier, where we took 20 people out of a population of size 100, every one of those sampled individuals would have the same sample weight of 5, because that's the inverse of this common selection probability of 2/10 or a fifth, right? 1/5 is the inverse of 5. 5 is the inverse of 1/5. Easy. So treating each person as if they represented 5 people in the population is a way of thinking about how you would expand your sample to represent the whole population. Now, for a general complex survey design, your sampling weights tend to be much more variable. But for purposes of an example, I'm going to show you how we might compute sampling weights in a simpler case. So let's return to our idea of a stratified population with these 4 strata appearing in these proportions. And to make things a little more realistic, let's pretend that our population is actually 1 million people in size, not 100. and we're going to be taking a sample of size 100, not 25, or not 20. So this table shows how the million people get allocated to your different strata. Okay? And now let's see what happens if we pull a balanced sample of 25 people from each of our strata. The final probabilities of selection for each sample person from each stratum are shown here in the third column, where I've scaled them by a factor of 1,000, and the fourth column shows the resulting weight, and here I've scaled it by 10,000. Now, it turns out that if you're looking to estimate means or distribution functions, it's okay to scale the weights this way because the scaling factor is going to cancel out in the estimation. But in some cases, you might actually want to estimate the actual number of people in the population with some characteristic, and then you'd have to bring the scaling factor back into play. Now, I want to point out that in this simple example, all the sampled members of the given stratum have the same sampling weight. And as I said before, in practice, this isn't going to really be the case in a complex survey. Instead, most of the time, each person is going to have a unique weight value. And this is because weighting for multi-stage samples is really complicated. It's still true that the individual sampling weights are the inverse of the final selection probabilities, but now the final selection probability itself has to take into account all the stage-specific probabilities of selection shown here in the lower equation. And there's even more reasons why these individual sampling weights tend to be unique. As part of the weighting process, we've already shown that stratification and clustering affect the weights, but you can also build in adjustments for different probabilities of non-response across the different types of clusters. And a minute ago I said that it's sometimes of interest to actually estimate a total number of people in the population with a given characteristic, and that has implications for how you would calculate the weights. You may or may not be able to use the scaling factors, or at least keep track of it. But what do I mean by that? Well, usually you want your sample to be representative of the population. And one way to kind of make that a more tenable assumption is to make it so that your weighted sample counts reproduce demographic characteristics of your population, say the numbers that are fallen into a given sex or age or race ethnicity group, and you might know those counts from a census someplace or some other outside estimation technique. Now, there's a technique called post-stratification that's often used in the survey literature that is used to ensure that your sampling weights satisfy this goal. And we'll talk about post-stratification a few more times later on. So to summarize this part of the talk, I've told you that complex survey methods are often used to collect data used for nutrition monitoring of large populations. And these complex survey methods can use some or all of stratification, clustering, and weighting. And in general, the stratification provides a way of balancing the precision of subpopulation estimates, whereas clustering decreases your sampling costs, but at the expense of precision. And that weighting is usually necessary to account for the effects of stratification and clustering, but it may also be used to account for additional adjustments that, for example, if you were making sure that your sample represents your population. So now I'm going to talk about some ways that you have to modify your approach to statistical analysis when your data come from a complex sample instead of the simple random sample that most of your techniques were originally developed for. So I've mentioned before that incorporating some or all of the complex survey design elements can affect the precision of your estimates. And I'll talk more about that later when I talk about standard errors. But it's also the case that, or before I do that, I want to talk about the companion to precision, which is bias. In practice, you have to account for the effects of all of the survey design elements that go into collecting the data you have on hand, because you want to make sure you get unbiased estimates and you want to get precise estimates. Okay? So I said before that the weighting helps you ensure the representativeness of your sample. And this means, like I said, that you need to take the weighting into account to make sure your sample-based estimates are unbiased for the parameters we're supposed to be estimating, the population-based parameters. So to show you what I mean about how this bias can happen, let's go back to our hypothetical stratified population example. Size 100, we're going to select 5 people from each stratum. Now on the left-hand pie chart, I've assumed the true mean of some characteristic of interest differs by stratum. The strata 1 and 2 having small values, signified here by saying mu equal to 4 and mu equal to 6, whereas strata 3 and 4 have larger values, 8 and 10. Now under our balanced stratified sampling scheme, we expect to get sample means within strata that are close to the corresponding values in the population. So in the right-hand pie chart, I've indicated this by saying my x bars are approximately equal to the same 4, 6, 8, and 10 values that we said were present in the real population. However, if we just take the unweighted sample mean, we're going to get a biased estimate of the population mean because our estimate will be dominated by the large values in the oversampled strata. I didn't actually show it on the slide, but here the population mean under this scenario is 6, but the unweighted sample mean would tend to average about 7, which is about a 16% overestimate. So I'll show you a real-life example of this a little bit later from NHANES, and you'll see this bias issue come up again. But before I get to that, I want to talk about, I'm going to sharpen up my previous statements about how survey sampling affects the precision of estimates by addressing specifically how the design elements affect the standard error of estimates. Well, what exactly do I mean by standard error of an estimate? In spirit, it's a measure that reflects the variation expected across repeated sampling of a population. So if you pick a sample from the population and compute some estimate of a population parameter, like the mean, and then you go back and select a different sample from the same population and repeat the process, you'll get a different value for the estimate because you pick different people the second time. Now, if your sampling scheme is doing what it's supposed to, most of the samples will yield estimates close to the true population value, and a few samples will yield estimates far away. And the picture at the bottom here shows graphically what I just said there, that the sampling distribution of the statistic has most of its mass near the population value and less mass farther away. Now, for a lot of estimators that have been proposed as a result of modeling techniques, it's been shown that under certain conditions, the sampling distributions are approximately normal. So this idea of most of the mass in the middle and a few at the ends, that's more rigorously, you can say it's actually normally distributed. Now, showing that this property, this normality property holds, is sometimes referred to as establishing a central limit theorem, or CLT, for the estimator. Now, this is the first time that I've actually used the word estimator instead of the word estimate, and I want to point out the difference between these two concepts. By estimate, I mean the number that you would actually compute from your sample data, and you hope that estimate is close to the population value. But by estimator, I mean the general statistical formula that you use to compute your estimates. For example, you can get an estimate of the median of the usual intake distribution using a variety of statistical methods. You could use the ISU method or the NCI method that we've talked about in earlier webinars. The numbers that you're going to get, the estimates, it might be very close for the two different methods, but the procedure used to obtain them can be very, very different. So we'll be very careful and we'll talk about the ISU estimator for the median usual intake or the NCI estimator for the median usual intake. So by definition, getting back to our standard error discussion, the standard error, or abbreviated SE, is the standard deviation of the sampling distribution of an estimator. So as a consequence of what I said before, the more independent pieces of information you have that are used to construct each sample estimate, the smaller the standard error. So if you're sampling 20% of your population each time, you'll have a smaller standard error than if you're only sampling 2% of your population each time you take a repeated sample. Also, if a central limit theorem has been established for your estimator, you can appeal the asymptotic normality to construct significance tests or confidence intervals. So probably everyone here has, at some time or another, constructed the confidence interval by adding plus or minus 1.96 times the standard error to a sample estimate. And that 1.96 is coming from this asymptotic normal distribution. So I've described the concept of standard error here as having to do with repeated sampling of the population. But in practice, you only get one sample. So to do significance tests or to make confidence intervals, you have to estimate the standard error from the data you have on hand. Now, it turns out that there's basic statistical theory that provides ways to estimate standard errors from sample data for a wide range of estimators. And when statisticians develop these methods, these theoretical things, they often use the words smooth versus non-smooth to differentiate between estimators that have well-behaved asymptotic properties and estimators that don't. So luckily, most of the estimators that we deal with in practice fall into the smooth or well-behaved category. For example, means and other what I call mean-like statistics, such as regression slopes or ratios of means. On the other hand, empirical percentiles, such as medians, or functions thereof, like interquartile ranges, are classic examples of the sort of non-smooth estimators for which standard error estimation is especially challenging. These kinds of estimators don't act sufficiently mean-like to permit easy derivation of central limit theorems, and their sampling distributions tend to be less well behaved. I'm not saying you can't establish the central limit theorem. I'm just saying it's not as easy as it is in the smooth case. So testing significance or constructing confidence intervals for these kinds of non-smooth estimators may have to be done using alternative methods where you can't necessarily rely on asymptotic normality. But the standard error, I want to point out, still retains its interpretation as a measure of the variation in your estimator over repeated sampling. Okay, so in the general complex survey scenario, when you've got strata, clusters, and weights in the picture, the behavior of the sampling distribution for an estimator is often derived by trying to formulate your given estimator as a function of weighted cluster means within strata, and then working with asymptotic distributions of those cluster means. So this gets back to the overall theme I started the section off with. You have to account for all the survey design factors, because that first bullet, you see it says cluster and strata and weight. So all three elements are in there. Now, I have to give you a little word of warning about the software that you generally use to do statistical analysis. Not all of it is what I would call fully survey aware. There are some statistical procedures that do allow the use of some sort of weight. You hear it talked about, for example, you hear about things like weighted least squares analysis, but they won't necessarily do what you need them to. So these types of procedures, they can do one of two things. They can treat the sample weight as a population expansion factor and just pretend that the observation that with a weight of 100 means that you have 100 observations with identical data that were in your sample. Or the weights might be treated as inversely proportional to the variance of the residuals in a regression. So these types of weighted analyses, they're called weighted analyses, but they may not properly account for the stratification or clustering that was done to actually get your sample. And this is because I said earlier that selecting clusters instead of individual units gives you fewer independent pieces of information. And in a complex survey, it's the number of clusters that's important, because those are the independent units, not the people within the clusters. So this concept of counting the number of independent pieces of information you have, well, statisticians formalize that in the notion of what we call degrees of freedom. So you may remember from your basic stats course, when you were testing the significance of a sample mean and your sample was real small, you had to look up the critical values in the t-table rather than the z-table for the normal distribution. And you looked at value, and that value that you looked up was on a line in the table where there was an index by the value that was indexed by one less than the sample size. That number, that n-1 number that you used to look up in your t-table, that was called the degrees of freedom. Now, when your mean comes from a general complex survey, n here is the total number of clusters. And you have to subtract 1 degree of freedom for each stratum, not just one overall. And that's what I've shown here in this equation in blue. So the implication of this is as follows. For the 4-year cycle of the NHANES survey from 2003 to 6 has over 20,000 individuals in it. But when you analyze the NHANES data, you treat it as if it were a stratified cluster sample with 60 clusters, 2 in each of 30 strata. And so now I say that you treat it this way. The actual sampling design of NHANES is kept secret to maintain confidentiality. But this 2-cluster per stratum pseudo design that NCHS, the people that run NHANES, provide, that works very well as an approximation. But in any case, the degrees of freedom that you see that you need to use in NHANES is only 30, which is not anywhere close to this 20,000 that you see on the first sub-bullet here. And this can make a big difference in the way statistical procedures report their significance tests if those procedures are not fully survey aware. So here's that real-life example I promised you earlier. So I'm going to look at total calcium intake for a subsample of women from the 2003 through 6 NHANES. The subsample is comprised of 2,601 women ages 31 to 70 who had a reliable first 24-hour recall. And the parameter of interest here is the population mean intake of calcium. And here I want to include calcium that comes from food and also calcium that comes from supplements. As Reagan's going to explain in the next webinar, the data I'll use for estimation are based on a combination of 24-hour recall data and data from the NHANES Dietary Supplement Questionnaire. Now, if you recall from webinar 2, you don't generally have to do a lot of complex modeling if all you want to do is estimate the mean usual intake for a group. Under the usual assumptions that we've talked about, you can just take the mean of your 24-hour recall data. But in SAS, the the software I usually use to do my statistical analysis, I can think of at least 4 ways to get an estimated mean and standard error for this set of NHANES data. And I've listed these 4 possible ways here. I can use the procedure univariate. I can use it by itself with no additional options, or I can have the choice of 2 other options that incorporate weights. I can either use a weight option or a freak option. And the freak option, FREQ, uses the population expansion idea and pretends that each real observation represents multiple identical observations where the multiple is given by the weight value. Or I can use one of SAS's fully survey-aware procedures. I chose survey means for this example. And the survey means syntax includes ways to specify all 3 elements of the NHANES design, strata, cluster, and weight statements. And I want to point out that only this last way incorporates all the design factors. So here are the results. You see, going down the second column, that the first way, the one that ignores the weights, yields a different estimate than the other 3 that take weights into account. So this is that bias issue that I mentioned before. But you also see differences in the third column for the estimated standard error, and in the fourth column, where this is the degrees of freedom that the procedures use to test whether the population mean was different from 0. I mean, that's not really a very important test, but it's one of the things that's produced by default in these kinds of procedures. But remember, only the last way correctly accounts for all the survey design factors. So only this last way has the right estimate and the right standard error and the right degrees of freedom, or at least as right as we can get from the sample estimate. So putting in the weights, regardless of how you do it, keeps you from making the approximately 8% underestimate the most naive approach produces. So that's why the last 3 rows in this table have the same estimate, but it's different than the first row. But the standard errors can be very, very wrong. In general, if you ignore the sample design, you get standard errors that are too small. So look at that 13 in the first row compared to 27. That's the more correct estimate. But depending upon how you treat the weights, I mean, if you want to say, I want to bring in the weights, I don't want to ignore them completely, but you bring in the weights, depending on how you treat them, you can get wildly different answers shown by the middle 2 rows. That in some cases, this population expansion idea really falls apart. And this is because the NHANES weight suggests there are about 70 million people, 70 million women, ages 31 to 70 in the population, and that's why that assumed degree of freedom is that 70 million number there. And that makes your standard error incredibly small and your significance values incredibly impressive when you look at the p-value for the test. Now this feature of the NHANES weights is due to that post-certification that I mentioned early on, where you want to make sure that you recover the actual count of some people with a given characteristic in your population. So this problem, where not all software is fully survey aware, is in part due to the fact that it takes a lot of work to actually extend statistical techniques that are developed for simple random sampling, to extend those to the complex survey case. And as you might have guessed from the examples I've discussed so far, it turns out that the simple estimators like the mean are the easiest to work with, and inference based on the classic t-test is relatively easy to extend to the survey setting. So survey statisticians have established these central limit theorems and standard error formulae for a lot of these mean-like statistics, and these have been incorporated into standard survey analysis software packages such as SAS or Sudan or Stata or R. But some statistical methods are more difficult to extend. The classic example here is that at least I'm not aware of any. I'm not aware of any survey analog to the likelihood ratio test that we often would want to use to choose between competing models in some of our modeling exercises. So the takeaway messages for this section of the webinar are listed here. First, it's important to account for any and all of the survey design factors when you analyze survey data. But your analysis tools might be limited because no one's previously extended them to handle these complex survey situations. And you're probably better off trying to see if simple t-tests or similar classic methods for which the central limit theory has been established in the complex survey case can be used to answer your research question. Because then all you would need in the t-test situation for inference is an estimated parameter and a proper estimate of its standard error. Now, I said proper estimate of standard errors. And that leads us to our next topic, and this is shown here in the outline, variance estimation in complex surveys. Now, the section, I could have just as easily called it standard error estimation in complex surveys, But if you ever wanted to get more information about this sort of topic, you probably have better results searching for variance estimation as your keyword. If you look at the standard textbooks on variance estimation and complex surveys, you'll find there's two basic approaches to variance estimation. The first is to use the method of Taylor linearization, sometimes abbreviated as simply linearization. And the second is to use a so-called resampling method. And I've listed some examples here, and I'll talk about them a little bit later. But first, I want to talk about Taylor linearization. This is a default approach that's implemented in most survey-aware software because it allows the use of textbook formulae to compute standard errors for estimators where someone's worked out the central limit theorem in the survey context. But for some of these new intricate estimators that we've been describing in previous webinars where for these measurement error models are used to estimate usual intake distributions, these textbook formulae don't exist, at least not yet. And back earlier in the webinar when I told you that percentiles like medians were the classic example of a problematic or non-smooth estimator, it turns out that in the particular case of Monte Carlo-based usual intake percentiles that we use in the NCI method, they're especially problematic to handle with this Taylor linearization approach. So we turn to the broad alternative of resampling methods. Now, in contrast to linearization, resampling methods don't need a textbook formula for every possible estimator that you want to consider. Instead, they provide an estimation framework that is theoretically shown to work for general classes of estimators like smooth or non-smooth or in some more complicated cases that depend upon some conditions on the kind of estimator you're dealing with. But the basic idea that underlies the theory of all the resampling methods is that you can emulate taking repeated samples from your population by repeatedly sampling from the data you actually have on hand. So you basically treat your sample as your population in miniature. And this idea reflects this spirit of standard error as being related to the variance of the sampling distribution or the variance of your estimator over repeated sampling. Now I'm first going to illustrate this idea for the bootstrap method, the non-survey simple random sampling case, just to keep this a little clearer. But then I'll talk a little more about what these sort of things mean in the complex survey setting. All right, here we go, about the bootstrap. Before I go on, I want to mention that this illustration of the bootstrap I'm going to be showing you is actually taken from a presentation by Anne-Claire Verneau, and I think it's really a nice illustration, so I wanted to make sure I gave her credit. And you'll probably see some other versions of these slides in later webinars because all the statisticians in the webinar series thought this was really, really cool. So, okay, to start off with, you have your original sample of data, and you use that data to compute your estimate, and I'll call it theta hat of the population parameter of interest, or theta. The bootstrap method says that you should then draw a replicate sample of the same size as your original sample using with replacement sampling. And if your random sampling scheme involves pulling names out of a hat, well, that means every time you draw a name for the replicate sample, you put the name back in the hat for the next draw. So this means that some people may appear more than once in the replicate sample, and some people might not appear at all. And then once you have your replicate sample, you use the same estimation procedure to compute an estimate based on the replicate sample. This kind, we'll call this theta hat 1. And you repeat this process many, many times, and you end up with capital B different replicate samples and capital B different theta hats computed from these replicate samples. And this number B, capital B, is usually a pretty big number, 200, 300, 1,000, or more in some cases. But then once you have all these estimates from your replicate samples, the sample standard deviation of those theta hats is the bootstrap estimate of the standard error of the estimate you computed from the original sample. So you pair up the estimate from the original sample with this measure of variability that's computed from the replicates. Now the key to the bootstrap method is this with replacement sampling. In fact, if you don't do your sampling without replacement, you're always going to get back the original sample. So it's important to allow the situation where in a given bootstrap sample, some individuals appear multiple times and some appear not at all. The reason I talked about the bootstrap simple random sampling first is in this last bullet. And I claim that the number of times an individual appears in a bootstrap sample is analogous to a sample weight, at least in this population expansion sense, because in the bootstrap, you actually get identical observations appearing multiple times in the replicate samples. And it's this property that really helps to implement the resampling methods for complex surveys, because we can operationalize resampling from the original sample by creating sets of weights for the original sample and for each of the replicate samples we want to draw. So in the Bootstrap example for simple random sampling, all the weights in the original sample were 1, but the individual weights, because each person appeared once in the original sample, but the individual weights created for the Bootstrap replicate, they vary according to the number of times a particular individual shows up. It might be 0, it might be 2, it might be 3, whatever. And this feature, this idea of operationalizing resampling by messing around with the weights is it eliminates the need to store multiple copies of a data set with a whole lot of analysis variables. You just have to add one additional weight variable per Bootstrap sample and a set of constant weights for the original or parent sample, and then you can use a weight-aware procedure, not necessarily fully survey-aware, but just weight-aware, to compute the Bootstrap estimates you need for estimating the standard error. And so you think of each set of these Bootstrap weights as a perturbed version of the weight set for the original sample, which were all 1. Now, all of the resampling methods that are applied to complex surveys can take advantage of this idea of implementing this resampling by weight perturbation. And the Bootstrap, the Jackknife, and the BRR methods that are applied to complex surveys, they differ in the numbers of weight sets that you actually need to do the procedure, the way you construct the weight sets, and the formulae for expressing the standard error estimate as a function of the variability among the replicate estimates. And those functions change because now you're talking about cluster sampling rather than simple random sampling. So it's not always just a simple standard error computation. You have to do some other, or standard deviation calculation. You have to do some more complicated formulae sometimes. So I illustrated the Bootstrap for simple random sampling, and I said you could do this replacement you could do the width replacement sampling by pulling names at random out of a hat. But when you try to extend the Bootstrap to complex surveys, you have to do your Bootstrap sampling according to the sampling plan used to draw the original sample. So in the general case, that means you have to mimic the drawing of clusters from strata and possibly post-stratifying all your replicate weight sets. Now, if the number of weight sets, your capital B, is very large, this can be very computationally intensive just to do the sampling, not to mention having to run all the analyses. And this computational burden is one reason that the Bootstrap is not as used as often in complex surveys as some of the other resampling methods. But it's kind of a shame, really, because the Bootstrap method has some really nice features. And one of those features is that it offers a robust method for constructing confidence intervals. So you can base the bounds of your confidence interval so that they bracket 95% of the Bootstrap estimates instead of taking plus or minus 1.96 times some standard error. And this may work better for poorly behaved sampling distributions of non-smooth estimators like percentiles, or for estimators like proportions where the asymptotic normality approximation only really starts becoming good for very large sample sizes. Now, I said the Bootstrap is not used as often as some of the other methods, but it does get used. In fact, it's actually recommended to use the Bootstrap for standard error estimation in Nutrition Cycle 2.2 of the Canadian Community Health Survey, and I'm aware of its use in at least 2 other applications of the NCI method for usual intake modeling. The first of these was a simulation study that was done by Dr. Janet Tews that showed that the Bootstrap does work for estimating model parameters and percentile estimates based on the NCI method. And based on that result, I recommended using the Bootstrap in some more recent joint work with Janneke Verkuyt-Kloosterman and her colleagues in the Netherlands, where we modeled usual intakes for young children based on data from the Dutch National Food Consumption Survey, and then we used the Bootstrap in that instance. So I'm going to talk about the remainder of the resampling methods, assuming I'm in the general complex survey case where I have strata, clusters, and weights. Okay, so now let me start talking about the Jackknife method. For the Jackknife procedure, you need to create one set of perturbed weights for each cluster in your sample. And the main idea of the Jackknife is to operate on only a few clusters at a time. So the kth weight set, here we'll say we have capital K clusters and index from 1 up to capital K, and we'll use a little k to indicate the indexing. So the kth weight set, when you go to construct it, deletes or assigns 0 weight to all the observations in cluster K. Now, when you've done this, you end up losing a chunk of weight because the cluster K is no longer in your sample. And so the Jackknife corrects for this by redistributing that chunk of lost weight among the other observations in the same stratum as cluster K, but it leaves the weights unchanged for all the observations and clusters from the other strata. Now, for surveys with many clusters, you still have to generate a lot of weight sets, but not as many as you would for the bootstrap. You don't need the 200, 300, 1,000 that you would for the bootstrap. And as I said before, you may want to be post-stratifying each weight set to your known subpopulation sizes. So, you know, there's less of this computational burden in doing, you know, that part compared to the bootstrap. Now, the theory of the jackknife says that it works with the same class of estimators that Taylor linearization works for, generally the smooth kind. And for purposes of usual intake estimation, this means it will work from model parameters instead of regression slopes, which is, as I said, one of the mean-like kinds of statistics. And back in my graduate school days, it seemed oh so long ago, I did some simulation studies and some theoretical work that showed that the jackknife could also be used to obtain approximate standard errors for usual intake percentiles computed with the ISU method because of the way that estimator is constructed. In some cases, it's smooth. But similar simulation studies suggested that the jackknife was not suitable for the Monte Carlo-based usual intake percentiles such as those used in the NCI model, or in the NCI method. Which is why the NCI method applied to complex surveys like NHANES usually uses the balanced repeated replication, or BRR method I'm going to talk about next. So the BRR method is one that's limited to the case of stratified cluster designs that have 2 PSUs per stratum. And for my purposes, that's fine because I've already said the NHANES, that's exactly the kind of sampling design you're supposed to treat NHANES as. And since a lot of work I do works for the NHANES survey, this is not really a limitation for me. So I said before that the jackknife operates on just a few clusters at a time. And the BRR, though, is much more aggressive in its perturbation of the weights. When you go to construct the kth weight set for BRR, you have to delete the observations in half the clusters and then make up for that by doubling the weights of the observations in the remaining clusters. And so there I would say the BRR uses perturbation factors of 0 and 2 as compared to the jackknife, which uses perturbation factors of 1, that is, no perturbation for most of the observations. But when you, well, for most of the observations. Now, it's true that when you want to have, that you always want to have at least 2 clusters per stratum to estimate standard errors. So jackknife perturbation factors can be as big as 2 if you have 2 clusters in a sample. But it may be much smaller, the perturbation factors may be much smaller if you get a lot of clusters selected in some strata. But regardless, because it perturbs a lot of weights at a time, I call BRR more aggressive than jackknife. Now, it turns out that the BRR method often requires fewer weight sets than the jackknife method. The exact number of weight sets you need for BRR is shown in the sub-bullet, and it's the smallest multiple of 4 that's strictly greater than the number of strata. And this kind of funny rule is a result of the way the weight sets are constructed. The choice of which cluster in a stratum to 0 or double is determined by the elements of what's known as a Hadamard matrix, which is a special matrix with elements of plus or minus 1 that's constructed to have orthogonal rows and columns. And these Hadamard matrices generally come in orders that are multiples of 4. So that's where that rule on that multiple of 4 business comes from. In the NHANES example where there are 30 strata, 30 strata, you need 32 BRR weights, but you need 60 jackknife weights because you have 2 PSUs per cluster. Now, this orthogonality property of the Hadamard matrix is used to ensure that no single cluster is disproportionately represented in the standard error calculation. The influence of each cluster is considered balanced, and that's where the name balanced repeated replication comes from. I said BRR is pretty aggressive. Sometimes it's too aggressive. You basically are throwing out half your sample for each weight set, and this means that standard BRR can sometimes be unstable due to these extreme perturbations. So a modified BRR method was developed by Robert Fay at the U.S. Census Bureau, and it uses less extreme perturbation factors. So instead of 0 and 2, Fay's method might use 0.3 and 1.7 as its perturbation factors. And then you don't throw people out, you just downweight them and upweight them. And as in the jackknife and bootstrap methods, you may still want to be performing some sort of post-stratification adjustments to each BRR weight set, like you would for the original sample. Now, for simple statistics like population means, you can use Taylor linearization, or equivalent of the jackknife. Remember, jackknife and Taylor are two ways of doing essentially the same sort of thing. To do analysis of usual intake data based on dietary data that come from the What We Eat in America portion of the NHANES survey. In fact, that's exactly what I did for my example. I used tailored linearization. Well, the VRR technique works for those cases too, but more importantly, VRR also works for those problematic Monte Carlo-based percentile estimates that the other methods didn't work for. So this has become the standard error estimation method of choice when we, meaning myself and colleagues, have applied the NCI method to NHANES data. So I want to summarize what I've said about standard error estimation in complex surveys. The standard survey-aware statistical analysis software typically uses tailored linearization to compute standard errors. And while that's limited to basic or mean-like estimators, it's really fast because it uses these textbook formulae. But for more complex estimators that are computed using techniques for which these textbook formulae aren't available, these resampling methods, Jackknife, Bootstrap, VRR, offer an alternative. So I want to give now some examples of what sorts of implications these survey design factors have when you actually want to do an analysis using these complex usual intake methods for getting distributions. So here's a typical research question you might want to answer. Based on my data obtained from this complex survey sampling plan, what's the usual intake of component X among subgroup Y in my population? Now, to answer this question, you have to consider several things. You have to consider the estimator of interest. Are you looking to obtain an estimated mean, an estimated distribution, estimated regression slope? Or you need to consider the method of analysis and the data requirements. You know, has this analytic method ever been applied in the context of sample surveys before? Do you have the right kind and amount of data for the method to be applied? Do you have enough replicate 24-hour recalls, or are you going to get by with just one 24-hour recall for a simple mean? And then lastly, you need to consider the technique that is going to be used for variance estimation and how to use the software to properly implement that technique. Is it something that you can use the standard survey analysis procedure for in SAS, Sudan, or something like that? Or do you have to use a special software package? And if that special package isn't survey-aware, how do you trick it into giving you results that you can use as part of, for example, a resampling approach to estimate standard errors? So here's how these considerations come into play for my earlier example about the mean usual intake of calcium. My desired estimator was the mean of the usual intake distribution, and the analytic method boiled down to computing the properly weighted mean of all the valid first-day 24-hour recalls from the NHANES data. Now, because the analytic method was so basic, I could use a default tailored linearization approach to estimate standard errors, and that's part of the common survey-aware software packages like SAS, Sudan, or Stata. I probably could have used R as well. Well, what if, for my second example, suppose I wanted to estimate the distribution of usual intake from my NHANES survey data, and I wanted to use the NCI method. The data I would need there are all the valid 24-hour recalls, not just the valid first-day recalls, and I've said for NHANES analysis, I would use the VRR method for variance estimation. Now, the SAS macros to implement the NCI method are partially survey-aware in that they perform weighted analysis, but you have to do some extra work to account for the stratification and clustering. Now, part of this extra work goes into constructing the VRR weights. The rest is in running the replicate analyses and actually computing the standard errors appropriately. Now, in the past, researchers at the Agricultural Research Service of the U.S. Department of Agriculture have constructed sets of VRR replicate weights that are suitable for this sort of analysis for NHANES for several different combinations of NHANES survey cycles. And now, in the past, these weight sets have been provided to various researchers that have been doing these kind of analyses, but we've been told there are plans in the works to make these weight sets more widely available. Right now, you kind of have to know someone who knows someone to get these things, and we're trying to change that and make it more available to the public. But for assuming you can get those weights, you can look at the advanced portion of the NHANES dietary web tutorial, which provides a detailed walkthrough of how you'd actually go through this analysis. Alternatively, you might want to estimate the distribution of usual intake from the Canadian Community Health Survey, and here you might want to apply the ISU method to, again, all valid 24-hour recalls from that survey. Now, as I mentioned before, Statistics Canada recommends using Bootstrap procedure, and they actually provide you with official Bootstrap weight sets just for this purpose. But since you're using the ISU method, you have to use the ISU software, either the original version, it's called SIDE, or one of the later versions, C-SIDE or PC-SIDE. All right, so we're coming to the end of this webinar, and I want to leave you with some key messages. First, as I mentioned way back at the beginning, the data that we use for monitoring usual intakes among populations are usually collected using complex survey methods, and I gave you some reasons why. I also showed you how the elements that give such methods the complex name, they affect the way that you have to compute point estimates and standard errors. And these elements, stratification, clustering, and weighting, all have to be accounted for. And I showed you that standard error estimation is an important part of dealing with complex survey data, and hopefully I gave you a sense of just how complicated it can be. Now, while means and mean-like statistics are handled easily by the default Taylor linearization method that gets implemented in your survey-aware software packages, there are some statistics like percentiles that are less well-behaved. And for those kinds of non-smooth statistics, I talked about alternative methods based on resampling, the BRR and the Bootstrap, that could be used. Now, remember that Jackknife is supposed to only work where linearization does. So depending on your estimator, you may or may not be able to use Jackknife as a resampling method for your given estimator. So finally, I want to stress that there is no one-size-fits-all approach to modeling usual intake from complex survey data. You really have to tailor your approach to your particular research question, the particular data that you have available, and the methods that you want to use to do the analysis. You have to know just how survey-aware your software is. If it can't handle the standard error estimation properly for a general complex survey, you might have to trick it into giving you some answers that are suitable for use in one of the resampling methods. And finally, your approach is really going to depend upon how much statistical expertise or support you can call on. And if you don't have access to a pocket statistician, then one good place to start looking might be the NHANES Dietary Web Tutorial, and that's one of the suggested resources for this webinar. All right, so I will close now, and we'll turn it over to Reagan for the question and answer session.
Thank you, Kevin. That was so informative. We'll now move on to the question and answer period of the webinar, and we already have several questions that have come in. The first is, for the examples that you provided on slide number 56, is the standard error for the survey means procedure similar to the standard error derived from the resampling method?
Yes, they would be very similar in almost all cases. The only time they're not going to be exactly the same or very close to the same is when if you do the resampling method, say using a Jackknife or BRR, and you post-stratify your weights, which is what's usually done, you'll get a standard error estimate that reflects resampling of a survey where you want to post-stratify. On the other hand, the SAS survey procedures generally don't account for this post-stratification idea, so it's possible that if the post-stratification makes a difference in your standard error, that your resampling method will give you a smaller standard error than the Taylor series would. But most of the time, they're going to be equivalent, yes.
Okay. Similar to that, would you get a similar standard error estimate to the survey mean procedure with all three of the resampling methods?
Yes. For survey means, since you're talking about a mean and it's one of those smooth statistics, all of your resampling methods are going to give you something that's pretty close to the Taylor series method because the estimator is so basic. Okay.
Someone asked if you could use the NHANES data without the weights, and would they still be considered nationally representative?
I think that the idea of nationally representative kind of boils down into saying, it kind of requires you to use the weights to really talk about nationally representative data in terms of counts and things like that. Now, some people have considered the idea of saying, well, what if I only care about some sort of biological mechanism between diet and health? And they may justify ignoring the sample and design that way and saying, these are people and this is biology and this is what it is. But most of the time, I think NCHS, the people that run the survey, and I think a lot of other people would say that you probably should think about using the weights if you really want to maintain this, if you really want to be safe in calling your results representative of the U.S. population.
Okay. Another question that just came in, do either the TOOS article or the Dutch publication demonstrate variance estimation for percentiles for episodically consumed foods?
No, it actually didn't in those two things I looked at, because we were looking at nutrients. But actually, I have done some simulation studies once before that showed that for episodically consumed foods, they do seem to, BRR does seem to work well for these percentiles. This was something I did for a presentation at one of the international conferences for diet and activity methods quite a while ago. So yes, I think that BRR is sort of your go-to variance estimation technique for when you have complex samples or complex surveys where you want to look at something like percentiles.
Okay. Moving on to the next question. Is the NCI SAS macros to construct BRR weights fairly straightforward to use, or would you need some experience in this area to understand and apply them properly?
Well, the NCI macros themselves we don't actually have macros posted yet to do the actual BRR weight construction. As I said, the people at ARS, the Agricultural Research Service at USDA, have, in most cases, provided the weights for us. I have constructed BRR weights before for parts of the survey, and I do have some internal macros that I think, as a group, we're going to discuss whether or not we need to make those available. But hopefully the actual use of the NCI macros for doing the variance estimation is explained quite well in the dietary web tutorial, the advanced section. So I think that's where you have a lot more information available.
I heard you use the phrase Taylor linearization in your presentation, and other people use the phrase Taylor series. Are those interchangeable, and if not, how do they differ?
They refer to the same general idea. I think in webinar 2 and maybe in webinar 3, we talked about expressing the mean or the variance in terms of a function of some data, and we use a Taylor series argument to say that a function of this random variable can be written this way. Taylor linearization uses the same sort of idea, so they are very, very similar in their yes, they are very similar, yes.
Okay. While we still have you in the hot seat, here's a few more questions. Can we use the resampling methods to estimate the means? And what advantages and disadvantages are related to that?
You can use the resampling methods to estimate the mean. They're usually going to give you about the same answer, and so if you have software you can get much faster. I guess the disadvantage of using the resampling method is it's much faster to use the Taylor series way than do the resampling in general. But if we go back to what I just mentioned a minute ago about what happens when you post-stratify your replicate weights, you can get an estimate that is a variance estimate that's a little smaller if you're using a resampling method with post-stratified weights versus if you were using just a Taylor series linearization from software that didn't take that post-stratification into account.
Okay. In bootstrapping, why do you use the point estimate from the original sample and not the replicates?
That's just because the bootstrap and the other things are technically variance estimation techniques. They're not necessarily point estimation techniques. The idea is that your estimate based on your weighted data that you get from the original sample is set up to be the best estimate it can be. And the only reason you're using Bootstrap or BRR or Jackknife is to provide a variance estimate. Now, if you go back and look in the survey sampling literature, you will find that the original derivation of the jackknife for complex surveys was actually designed to do some sort of a bias reduction. Most of the time, and we don't treat it that way for purposes of variance estimation, because when we're using it as a general variance estimation technique, all we want to do is use it to estimate the variance. We want to take our point estimate from the full sample and treat that as our estimate of the actual parameter of interest.
Okay. What makes the Canadian Nutrition Survey fit for the ISU bootstrapping method and not the BRR method?
Well, I would, if I had my brothers, I would hand it off to Sharon Kirkpatrick, who actually has done a lot of work with the Canadian survey, but apparently, if I understand it, and Sharon is sitting right here, so she'll tell me if I'm right, in order to analyze the Canadian data with the bootstrap weights, you actually have to go to the research center and do your results there, and they have things set up in a certain way that it's better to use the bootstrap that they provide as opposed to trying to write up your own, develop your own BRR weights and use those and put them all together in the right way. It's just not, I mean, technically, if you had unfettered access to the data, you probably could do BRR instead of bootstrap, but you would have to construct those bootstrap weights yourself, whereas Stats Canada provides official bootstrap weights for use in the with its data. And the reasons you have to go, the reason you don't have unfettered access to the data is a confidentiality reason, again, coming in. So you don't actually, so in general, people aren't going to have the data they need to actually construct BRR replicate weights. Because they don't have access to the confidential sampling design. So you end up being, again, coming back to the use of using what's officially provided, which is the bootstrap weights.
Okay. What sample size do you need to be able to generalize to the U.S. population?
That is actually a question that is best answered by the people who run the survey, who run the NHANES survey. And I just pointed out what the sample sizes are for about 20,000 people in a 2-year cycle. I think it tends to get bigger over time, but it's the number of people that you need depends upon a lot of competing factors. You need to know. You need to think about how you're going to collect people, but also how you're going to do the multi-stage sampling, how you're going to allocate your resources to driving all over the country to pick people up, to get them to come to the MEC. All these different things have to be incorporated into into your final decision. And NHANES, or the NCHS people that actually draw the sample, those are the ones that really could better answer this question. All I can say is that we take the data we have at hand from NHANES and we use it, and we estimate our standard errors for it. And when the standard errors say that this estimate is not very precise, we don't report it because there weren't enough people to actually answer that particular question for that particular segment of the U.S. population.
Okay. This is a comment. I just wanted to remind everyone that the links to the NHANES dietary tutorials, including the advanced dietary tutorial, are under the recommended resources, and the links are provided for those. And we can also add key resources to the website. At this point, it looks like most of the questions have been answered, and I would like to take this opportunity to thank Kevin and to thank you all in the audience for participating in today's webinar. Please join us next week for Webinar 5, where I will be discussing the estimation of distributions for total usual nutrient intakes from the diet and dietary supplements. Thank you very much, Kevin.
Thank you.